Bismillahirrahmanirrahim. In this course module, we will talk about Gram-Schmidt orthogonalization, that is also known as Gram-Schmidt process. It is a procedure that takes input non-orthogonal, linearly independent set of vectors and constructs orthonormal vectors. So we will talk about a brief overview of this Gram-Schmidt process. How does it connect with the concepts such as linear independence and orthonormal vectors, which we studied in the previous module. Then I will explain the algorithm of this Gram-Schmidt process. I will also explain the geometrical interpretation of the working of the algorithm. And finally, we will conclude with one example. Okay, let's start with a quick overview of this Gram-Schmidt orthogonalization process. In the previous module, we talked about the concept of linear independence and orthonormal vectors. So given a list of vectors, so how do we determine whether the list of vectors is linearly independent or not? So to answer this question, we can use this Gram-Schmidt process. Also, we talked about the significance of having orthonormal vectors. So given linearly independent vectors that are non-orthogonal, this Gram-Schmidt process allows us to construct orthonormal vectors that span the same space that is spanned by non-orthogonal linearly independent vectors. So how does it work? So this process takes input a list of vectors, and if these vectors are linearly if this list is linearly independent, right? So assume that if linearly independent, in this case, this process constructs orthonormal vectors, the same number of orthonormal vectors q1, q2, qk, and if these vectors belongs to Rn, these orthonormal vectors also belongs to Rn, right? So okay, and these orthonormal vectors q1, q2, qk has some very nice properties. So the property is that, say, for each ai is a linear combination of q1, q2, first qi orthonormal vectors. This also informs you that if, say, any ai is linearly dependent on the vectors a1 to I minus 1, then qi would be 0, right? Or we can say this algorithm detects, so if a1, a2 up to, say, aj, this list is linearly independent, and if you add another vector to this list, say when you add aj plus 1, so this list becomes linearly dependent. So if this is the case, this Gram-Schmidt process can detect the presence of linearly dependent vector in the list. Okay, let's talk about how does this algorithm work, and how does it compute orthonormal vectors, and how does it detect linear dependence in the list. As we said earlier, that this algorithm takes input a list of vectors a1 to ak, and then say this list belongs to Rn, and the output of algorithm is There are two outputs. The first one is that this algorithm detects linear independence, and if the vectors are a1 to ak, if these vectors a1 to ak are linearly independent, then this algorithm produces orthonormal vectors q1, q2, qk that belongs to Rn. Okay, let's talk about how does this algorithm work. So let me explain the steps of this algorithm. So this is an iterative algorithm. So it starts from say I is equal to 1, and it first computes q1, and then it computes q2, and so on and so forth. So it has k number of iterations. Say start from, say, for I is equal to 1 and 2 small k, and it has two steps, right? So in the first step, we compute qi tilde, that is given by this, and in the second step, so we simply normalize qi tilde to obtain qi. So this is qi tilde, and then we divide by qi tilde norm, so you get qi. So there are special names to these two steps. So the first step is referred to as orthogonalization, because this is the main step. In second step, we are simply carrying out normalization, right? Let me explain the working of this algorithm, right? So maybe for better understanding, we run this. We take k is equal to 3, and we run this algorithm for k is equal to 3. So we have three vectors a1, a2, a3, and which are non-orthogonal, and we run this Gram-Schmidt process, this two-step process, for I is equal to 1, 2, and 3. So when you take I is equal to 1, so what do you get here? So see, if you see this summation here, the summation runs from j is equal to 1 to I minus 1. When I is equal to 1, so this summation would run from, so j is equal to 1 to 0. That means this summation would not contain any of the term, or you can say q1 tilde would be simply a1, right? So you can say q1 tilde is a1, and once you have q1 tilde, simply divide by the norm of q1 tilde to obtain q1. So q1 is normalized a1, right? So okay, so once we have q1, so we run the second step. When I is equal to 2, so q2 would be given by simply a2. In this summation, we will only have one term, so we'll run from j is equal to 1 to 1. We only have one term, right? So the first term is okay, on the right hand side we have a2, and from a2, so what do we subtract? So we subtract q1 transpose a2. So what is this term? So this term is this is the projection of vector a2 on q1. So this will be a scalar because it's inner product, and we scale q1 with this projection, right? And from a2, when you subtract this quantity from a2, so what you get is a vector that is orthogonal, that is not orthonormal, that is orthogonal to q1. And when again you divide q2 tilde by q2 tilde norm, you get q2 that is orthonormal to q1, right? So and then you run for k is equal to 3, so you get q3 tilde as a3. You subtract okay, now we can explain this term, right? And then we can connect with what we had here, right? So this term is in fact a projection of, or you can say the components of A3 uh, that are that can be expressed as a linear combination of Q1 and Q2, right? So you can say A3 has three components, right? The first component along Q1, the second component along Q2, and third component along Q3, which we want to determine, right? So we first find out what is the component along Q1, and that is given by this term, and the second component of A3, that is along Q2, that is given by this component. So you add those two components, and since those two components are orthonormal to each other, so orthogonal to each other, and then you subtract those two components from A3, and you get the contribution of A3. In fact, you get Q3, and that's the third component of A3. And Q3 has a nice property that Q3 would be orthogonal to Q1, and so Q3 tilde would be orthogonal to Q1 and Q2. And when we divide Q3 tilde by its norm, we get Q3. So after running these three steps, so what you get is Q1, Q2, Q3 that are orthonormal to each other. So, but you will only get Q1, Q2, Q3 if A1, A2, A3 are linearly independent. What happens if, say, A1, A2 are linearly independent, and when you add A3, A3 is a linear combination of A2 and A3. If A3 is a linear combination of A1 and A2, then so what you get here, so this term would be exactly equal to A3, and when you subtract from A3, so Q3 would be 0. When Q3 tilde is equal to 0, Q3 is equal to 0, that indicates that when you add A3 is a linear combination of A1 and A2. So we can say that, so we can test linear independence so between these two steps, right? So we can say after running the orthogonalization step here at this point, if Qi tilde is equal to 0, so we can say linear dependence detected. So algorithm detects linear dependence. So between these two steps, so this is the point where you can check for linear dependence. Okay, let me also try to explain this geometrically or graphically. So we take two vectors, A1 and A2, and we know that Gram-Schmidt process is a two-step process. The first step is orthogonalization, and the second step is normalization. Right? So we have two vectors. That means we'll have two iterations of the algorithm. We start with k is equal to 1. We'll start with iteration 1. Right? So what will happen in iteration 1 in orthogonalization step? So Q1 tilde would be A1. That means so this vector A1 would become Q1 tilde, right? So this circle here is, so this represents a circle of unit radius. That means when you normalize any vector, so that would lie on this circle. So in the first iteration, in the first step, Q1 tilde is A1. This red is Q1 tilde. So what is the second step in the first iteration? Normalization, right? So you normalize Q1 tilde and make it Q1, right? So what you get is this. So Q1 is Q1 tilde divided by the norm of Q1 tilde, and you get this Q1. So this is the first iteration, right? Now we have Q1, and now we're on the second iteration, right? In the second iteration, so what should be the step? So we want to find out Q2 tilde first. So we run this orthogonalization step, and since k is equal to 2, so we will have this equation. So Q2 tilde would be A2 minus the projection of A2 on Q1 times Q1. You subtract this from A2, right? Okay, let me explain this graphically, right? So we are here, so this is Q1 and this is A2, right? So what is this quantity Q1 transpose A2? So the projection of A2 on Q1 in the direction of Q1. So this quantity here is the projection of A2 on Q1 in the direction of Q1, right? That would be simply given by, so, and you take a minus of this. So this vector, this black vector here is minus Q1 transpose A to Q1. And when you subtract this from A2, so what you get is Q2 tilde. And since you have subtracted the component, this black one, so Q2 tilde would be perpendicular to or orthogonal to Q1. And then you carry out just simply now this normalization step. You scale back this Q2 tilde on this unit norm radius, and what you get is Q1 Q2. So we started from say here, right? This is a starting point, right? So in the first iteration, this is orthogonalization, and this is orthogonalization, this is normalization, and in the second iteration you get this is orthogonalization and this is normalization, right? And this is, we can say this is, so we have obtained two orthonormal vectors. Okay, what will happen if I add another vector, right? Say if I add another vector, so now we take k is equal to 3, and in fact we say A3 would be a linear combination of A1 and A2, right? So there won't be any changes in iteration 1, iteration 2, so you will eventually reach here, but here now you will have this another vector, say it should be drawn here. This is the same A3. That is a linear combination of A1 and A2, and it's also a linear combination of Q1 and Q2 as well. Okay, so now when you run this step of orthogonalization in iteration 3 to find out Q3 tilde, since A3 is a linear combination of Q1 and Q2, so Q3 tilde would be A3, and when you write this equation, what you get here is exactly A3, and eventually Q3 tilde would be 0, and this Q3 tilde 0 indicates that A3 is a linear combination of A1 and A2. Let me also try to explain this with the help of one numeric example. So we take one example in which we take two vectors in R2, A1 is 4, 3 and A2 is minus 2, 1. The two vectors are linearly independent because A2 is not a scalar multiple of A1. So we want to carry out a Gram-Schmidt orthogonalization. So the first step would be the first step in the first iteration. So the first iteration we have I is equal to 1, and the first step is orthogonalization in which we take Q1 tilde is equal to A1. So Q1 tilde would be given by 4, 3, and using Q1 tilde we can find Q1 in the second step, that is normalization. So Q1 is given by Q1 tilde divided by the norm of Q1 tilde. So norm of Q1 tilde would be given by 16 plus 3, 25. So square root of 25 would be 5. So 1 over 5, 4, 3. So this is Q1 after first iteration. So in second iteration, I is equal to 2. So you find Q2 by first finding Q2 tilde. So Q2 tilde is given by A2 minus Q1 transpose A2 Q1. So the projection of A2 on Q1 in the direction of Q1, you subtract this from A2 and you get Q2 tilde. So that will be given by minus 2, 1 minus, so Q1 transpose A2. So Q1 is 1 over 5, 4, 3, and A2 is minus 2, 1. So what you get is this 1 over 5 times 4 to the minus 2, minus 8. It would be minus 1. So this inner product is minus 1. So you get plus Q1, that is 1 over 5, 4, 3. When you simplify this, what you get is Q2 tilde would be 1 over 5 minus 6 and 8. And simply Q2 would be given by Q2 tilde divided by Q2 norm of Q2 tilde. So norm of Q2 tilde would be given by 36 plus 64, 10, square root of 100 is 10, by 5 is 2. What you get is 1 over 5 minus 3 and 4. So this is Q2 tilde. This is Q2. So Q1 and Q2 are orthonormal vectors. They are unit norm and they are orthonormal to each other. And so A1 and A2 were not orthonormal, but Q1 and Q2 are orthonormal. We stop here. In today's module, we have talked about a Gram-Schmidt process that can be used to construct orthonormal set of vectors for a given list of non-orthogonal linearly independent vectors. If the given list is linearly dependent, Gram-Schmidt process can be used to detect such linear dependence. We will again talk about this Gram-Schmidt process when we will discuss QR factorization of matrices. We stop here and we'll continue in the next module. Thank you very much.